So in this question, we're given two vectors. V is negative 3, 2, 2, and W is 1, 4, negative 6. And we're asked to find a unit vector perpendicular to both V and W. So first of all, let's ignore the part about the unit vector first, and first think about how we would find simply a vector that is perpendicular to both V and U. Well, the obvious way to do that is to use the cross product, because if we take the cross product of V and W, the cross product always returns a vector that is perpendicular to the two input vectors that we're doing the cross product on. So let's call the vector that we get from doing the cross product of V and U, let's call that vector A. Let's figure out what vector A is, and then we'll turn vector A into a unit vector. So we come over here to the side, we've got our I, our J, and our K components. I'm going to do negative 3, 2, 2, and then 1, 4, negative 6, and then I'll make copies of my I and my J, and then I just need to remember the pattern that I follow while I'm doing the cross product here if you're using this method. So what am I going to get here for my x component? I'm going to get 2 times negative 6, which is negative 12, and then I'm going to subtract 8 from it. So that's going to give me negative 20. For my j component, I'm going to do 2 minus 18, which is negative 16. And then for my k component, or my z component, I'm going to do negative 12 minus 2 is negative 14. So I have this vector, negative 20, negative 16, negative 14, which is perpendicular to both V and W. Now, that's not the only vector that is perpendicular to both V and W. Any vector that is a scalar multiple of this will also be perpendicular to V and W, because it'll be parallel to that vector A. So I could instead define another vector V, and as long as B is a scalar multiple of A, it is also perpendicular to V and W. So I can take each of my components here, and I guess I could divide them by negative 2 to get 10, 8, and 7. So because A and B are scalar multiples, B is just, A is negative 2 times B. B is also perpendicular to both of them. So now we can take one of our vectors here and we can turn it into a unit vector. So if we want to find, let's say, B hat, we are going to take our vector B and divide it by its magnitude. So let's figure out the magnitude of vector B. That's going to be square root of 10 squared plus 8 squared plus 7 squared. That's going to be 164 and then 49. So that's going to be square root of 200 and, oh, sorry, 13. Let's do that again. 100, 164, 204 plus 9 is, 213. Okay, so our unit vector, B hat, is going to be 1 over square root of 213 times this vector B, 10, 8, 7. So just doing the scalar multiplication, we're going to get a vector that is 10 over root 213, 8 over root 213, 7 over root 213. So B hat is our unit vector that is perpendicular to both V and W. Now, this last thing it says to do is to check using the dot product. So we could check it using the dot product just by making sure that if we do the dot product of B hat with any of those vectors that we put in, either V or W, we should get 0 out if those two vectors are in fact perpendicular. So let's do, just to quickly check, B hat dotted with, let's do vector V. So that's going to be 10 over root 213, 8 over root 213, 7 over root 213, dotted with vector V is negative 3, 2, 2. Okay, so let's do the dot product here. I'm going to pull out the 1 over root 213. And let's see, I'm going to get negative 30 plus 16 plus 14. Negative 30 plus 16 plus 14 is 0, so this is in fact 0. So these two vectors are in fact perpendicular. So B hat is our unit vector that is perpendicular to both V and W.